Let's now work out the mathematical formula for the rate at which time slows on a moving clock. Again, just to get us on the same page, what's the essential idea? What we have seen is that the elapsed time on the moving clock differs from the elapsed time on a stationary clock. That just comes from considering the lengths of the paths that the light takes in each of those clocks to go tick and tock. And again, we're framing this in the language of light clocks, but it is true for any clock. Light clocks are only special that they allow us to see their internal mechanism so clearly that we can easily figure out how quickly time slows on the moving clock. Okay, so what we then therefore need to do, according to what we've already established, is we just need to calculate the lengths of the trajectory in the moving clock from our perspective versus the length of the trajectory in the stationary clock from our perspective. Okay, so let's just set this up similar to what we did before, but now we're going to put some mathematics behind it. So there goes the tick trajectory, and there's the tock trajectory. We will again call this length d, and if we're looking at the guy going up and down in the stationary clock, let's say this guy is over here. Let's call that length equal to L. So our goal is to calculate d divided by L. That's what we want to calculate. How do we go about doing that? Well, let's note that if this angle here is theta, then we're in the happy situation that we've got a simple right triangle at our disposal. So if I drop this guy over here, then I note that d over L can simply be gotten from looking at sine of theta, right? Because sine of theta is given by L over d, right? So that means if I look at sine theta to the minus 1, this will be equal to d over L, as we wanted. So the calculation of d over L comes down to calculating sine theta and flipping it upside down. So how do we calculate the sine of that angle? Well, here's the key idea. As the light is traveling from here to there, we know that its speed, of course, is equal to the speed of light in that direction. Now, as you will recall from doing components of vectors in basic geometry or trigonometry, if the speed of the light is c going in that direction, then it devotes a component of its speed equal to c times cosine theta in the horizontal direction. So this is the horizontal component of the light's speed. Now, the reason why I'm interested in the horizontal component of the light speed, again, the speed of light is c, but its progression in the horizontal direction is given by c times cosine of theta. Again, cosine is the adjacent over hypotenuse, so that gives us the projection of that speed into the horizontal direction. This must be equal to the velocity v of the clock itself, right? Because that's the only velocity for which the ball of light will keep perfect pace with the moving clock, which we know it must, because again we can give the argument that the stationary person sees the clock moving, but the person moving with the clock, from their perspective, the clock isn't moving at all, and therefore from their point of view it must be the case that as you're going along, right, as you're going along, the ball of light must be moving in the horizontal direction at exactly the speed of the clock to keep pace with it. That ensures that the ball will go up and down, as we know that it does. So this is a cool little formula over here, because if v is equal to c cosine theta, then that means that cosine theta is equal to v over c. So given v, the velocity of the clock, we can get cosine theta, not exactly what we wanted. We wanted sine theta, but that's fine, because you will also remember the famous little formula that is really just the Pythagorean theorem, slightly disguised, that sine squared theta plus cosine squared theta is equal to 1. And that being the case, we can now write that sine squared theta is equal to 1 minus cosine squared theta. And from cosine theta equals v over c, this guy is equal to 1 minus v over c squared. So sine theta is the square root of that. So that's the square root of 1 minus v over c squared. And then finally, flipping that upside down, sine theta to the minus 1 is equal to 1 divided by the square root of 1 minus v over c squared. And sine theta to the minus 1 is, in fact, d over L. So that, therefore, tells us that d over L, what we're after, is nothing but 1 over that quantity, square root of 1 minus v over c squared. And that is deserving of being called out, because that now is a derivation of the rate at which time elapses on the moving clock compared to the rate at which time elapses on the stationary clock. And that is this factor that we call gamma that we mentioned earlier on. And what I'd like to do is now show you a somewhat cleaner version of that derivation, because this is such an important point that it's worth seeing it done systematically more than once. And here is a video version of the same derivation. So there's the moving clock, and there's the main point, that the component of the velocity of that light in the horizontal direction must be equal to the velocity of the clock. And the horizontal component of the velocity of light is just gotten by taking c times cosine theta. And once you know that that's equal to the velocity of the clock, you are home free, because now we can just solve for cosine theta, given that, and the result between sines and cosines, as I mentioned before, you can go ahead and solve for sine theta, solving therefore for 1 over sine theta. And 1 over sine theta is nothing but the ratio that we are after. And therefore, we get our result, the gamma. The relationship between the elapsed time on the stationary clock and the elapsed time on the moving clock is simply given by 1 over the square root of 1 minus v squared over c squared, this famous time dilation factor gamma. So let's take a quick look over here. What I'm showing in this demo, and again, play with it at home to get a feel for these results, is a plot of gamma versus the velocity of the clock, the velocity of the ship, whatever object is moving. I'm going to always plot that velocity in units of the speed of light, so we can choose the speed, say, of the spaceship in this case to be 29% of the speed of light. And if you calculate gamma at that speed, you have something that's bigger than 1, but not a whole lot bigger. And 1 over gamma is a number that also will come into all our calculations, so you should have a feel for it too. And the point of this little demonstration is to note that gamma stays very, very close to 1. It's always bigger than 1, right? So bear that in mind. We have over here, it's 1 over the square root of this quantity. This quantity itself is always less than 1, so this ratio is always bigger than 1. There's always more time elapsing on the stationary clock compared to the moving clock. So gamma is always bigger than 1. But how much bigger is it than 1? And that we see here is that it doesn't get much bigger than 1 until, look at the steep rise in this curve over here. When the speeds get close to the speed of light, then it takes off and it shoots up. And in this graph, it doesn't get any bigger than 20, but it can be as big as you want, because again, as v gets very, very close to c, this gets very close to 0, and 1 over 0 soars to infinity. And this now allows us to go back to the demonstration that we looked at before and understand it in quantitative detail. So you played with this earlier, in which you saw that time on the moving clock goes off slow from the perspective of the stationary clock, but you didn't know the math behind this. Now you do. And to signify that, this demonstration now also has the time dilation factor. This is actually 1 over gamma that we are showing here, the right-hand graph that was on the previous demo. And again, as the velocity gets very close to the speed of light, 1 over gamma gets smaller and smaller, which means less and less time elapses on the moving clock compared to the stationary clock. This is the essence of time dilation.